Now that the overburden has eroded away, the Pluton, in a sense, remembers that former pressure and is pushing up against nothing, and it can pop the rock, causing what we call exfoliation domes, such as these that we see in Yosemite. The cracks may look like a kind of onion layering, but it's really pressure release fractures. Besides the blobby and blister shaped plutons, we can have cylindrical vents and sheets like dikes and sills. All lava flows at the surface are fed by a vent or a dike. The vents have basically cylindrical or circular shapes that intersect the surface in circular patterns. The dikes are tabular in shape, that is, they have two long dimensions and one short, giving them an overall sheet appearance. Sills are also tabular in shape, and we distinguish between sills and dikes by the way they cut across the country rock. If the country rock has layers, and our tabular igneous body cuts across those layers, not parallel, we call it a dike. We can say a dike is discordant with the country rock structure. Conversely, if the igneous intrusive rock body is tabular and concordant, that is parallel with the country rock layers, we call it a sill. We can almost think of a sill as an underground lava flow running along the bedding planes. Both sills and lava flows often are fed by dikes, which we call feeder dikes, but we can tell a sill from a lava flow. One way we distinguish is crystal size, as sills are coarser grained than lava flows. We can also look for something we call a baked zone, where the magma body dumps heat into the surrounding rock and alters the country rock without melting it, bakes it. Because the heat to bake the country rock comes from the outer surfaces of the magma body, there is also a chill zone in the igneous body where smaller crystals line the edge of the pluton, and the crystals get larger towards the center of the pluton and smaller towards the edge. A sill, underground, will bake the rock both above it and below it. A lava flow will bake the rock below it, but there is nothing but air above it, so it can't have a bake zone on top. We also see more bubbles or vesicles in lava flows that have reached the surface and had their confining pressure released, like opening a soda can, while a sill is like a soda under pressure that's kept its bubbles in solution as the magma froze, so few to no bubbles in a sill. Dikes are usually more resistant to erosion than country rock at the surface and stand out as linear ridges. The same is true for vents and pipes and sills. The more circular shaped conduits for magma to the surface will result in some interesting features. Sitting somewhere between intrusive and extrusive, volcanic plugs are formed from more resistant igneous rock which froze in the central vent of a volcano and which erodes away more slowly than the volcanic flanks of truly extrusive material. The neck of the volcano can resist erosion to remain behind as a striking example of differential erosion and symbol of extraterrestrial encounters. Forget extraterrestrial, let's just deal with extrusive right now. When magma reaches the surface, we can get lava flows, which fall into two broad categories based on their relative viscosity. These flows are much more common on the mafic end where the lava can flow, and though still present at the felsic end, lava flows give way to pyroclastics, fragmented ejecta when silica content and thus viscosity of the magma increases. When a magma is first ejected onto the surface as lava, it has a relatively high temperature and dissolved gas content, which helps it have a lower viscosity and run freely as the surface of the lava freezes into a crust, which gets wrinkled and finally freezes through into a pattern we call smooth and ropey. This type of lava is known as pahoihoi, but as the lava flows downhill, it cools and expels dissolved gases, making it more and more viscous. As viscous lava finds resistance to running freely, it begins to freeze blocks at its surface that get jumbled together in a jagged, rough, and blocky surface. This is what we call lava. Because lava flows cool from the top down and thus contract from the top down, they start cracking at their tops, and these cracks propagate downward into the base of the lava flow, in the process making columns that break from each other without moving relative to each other. If a break in a rock has relative movement, we call it a fault, but these breaks with no relative movement are called joints. And as lava flows make joints, which turn a solid lava flow into a series of columns, this is called columnar jointing, and is a rather reliable way to tell a lava flow layer from a sedimentary layer from a distance. There is a possibility for a lava flow to cool from the bottom up instead, as when it runs over a wetland or stream. The water turning to steam below the flow can cause the lava to freeze and break in a tumultuous way and result in the feature we actually call a tumulus. When you look at these from the right perspective, you really understand why it's called a tumulus. Remaining at the surface, but stepping away from lava flows, we see the fragmented ejecta which coalesce to make our pyroclastic rocks. These come mainly from ash clouds that rain down on an area, or the larger cousins of ash, lapilli, cinders, and bombs, which accumulate closer and closer to the volcanic source as the ejecta gets larger and larger. Ash, being the smallest pyroclast, can actually travel all the way around the world. Now, some of the close to the source pyroclastics come from the most deadly volcanic manifestation, the pyroclastic flow. It can kill you with heat, impact, or suffocation, but when it finally settles down, it can also fuse around you into a volcanic tuff if we have pure ash, or a volcanic breccia if we see larger angular fragments frozen within. And pyroclastic flows make for a killer ending this week as we round off our discussion of the igneous rocks. When we come back next time, we will move on around the rock cycle and begin our investigation of the sedimentary rocks, the layered pages of our planet, here on Earth Explorations.
Guess what? I'm back. And this time, it's volcanoes. Born out of tectonic plate movements and magma, volcanoes are the creator and destroyer of life on Earth. Formed by rising magma originating in the core of the Earth, volcanoes are the most powerful and destructive force on this planet. Part of a global system constantly changing and reshaping our world. But in this video, we're going to focus on intrusive activity. Intrusive volcanic activity takes place beneath the Earth's surface. When magma is forced to rise to the surface, only a small amount of it actually makes it to the top. The majority of the magma is intruded into the crust, where it solidifies and forms a range of features. Dikes are vertical intrusions which cut across the layers of rock. They often occur in groups, which are known as dike swarms. Many Scottish islands, such as Mull and Skye, have dike clusters associated with them. Sills, on the other hand, are horizontal intrusions which go between the different layers of rock. Erosion can expose intrusive activity and bring it to the surface. Batholiths are a great example of features which can be exposed through erosion. They are formed deep below the Earth's surface when magma cools and solidifies, forming large crystals in the rock, such as granite. Batholiths are often dome-shaped and can be exposed by erosion, such as the batholith in Hambledown Tor on on Dartmoor.
Now I'm going to show you some videos which are related with the earthquake. In our syllabus, earthquake is one of the important unit on which the several questions are always asked. I'm going to cover that point later on, but today just I will show you the points which are included in our syllabus with the help of these videos.
The motion we feel on the surface of the Earth during an earthquake comes from energy released deep within the Earth. This energy is transmitted to the surface by earthquake waves. The study of earthquakes and earthquake waves is called seismology. Earthquakes occur when rocks deep underground suddenly break under pressure or slip along a fault. The point of release is known as the focus of the earthquake. The energy released by the earthquake radiates from the focus as body waves. There are two types of body waves. The fastest wave is called a P wave, or primary wave. It moves between 4 to 7 kilometers per second, depending on the density of the rock it's moving through. A P wave is a compression type wave. Rocky material in its direction of travel compresses, then expands as the wave passes. A P wave is similar to a wave traveling through a spring. The coils compress and expand in the direction the wave is traveling. The second type of body wave is called an S wave, or secondary wave. It travels at about 2 to 5 kilometers per second through rock, about half the speed of a P wave. An S wave is a transverse shear wave. Rocky material in its path moves up and down, or side to side, perpendicular to the direction of the wave's travel. An S wave is similar to a wave traveling along a piece of rope. The wave moves along the rope by moving a section of the rope up, then down. Surface waves radiate outward from the epicenter, the point on the surface closest to the focus. Surface waves are slower than body waves, traveling at 2 to 3 kilometers per second. They can change the surface of the Earth as well as damage homes, buildings, and other structures. There are two types of surface waves. A love wave causes side-to-side motion perpendicular to its direction of travel. It can cause damage by breaking roads and pipes. The second type of surface wave is called a Rayleigh wave. It moves the surface of the Earth up, forward, down, and back in a circle. It can cause damage by knocking buildings off their foundations. In most earthquakes, combinations of love and Rayleigh waves cause the most destruction because the ground shakes up and down and side to side at the same time.
Earthquakes. An unexpected movement of the Earth's surface is called an earthquake. When two parts of the Earth's surface move suddenly in relation to each other along a fault line due to tectonic forces, an earthquake occurs. A tremendous amount of energy is released in the form of tremors and vibrations. Such earthquakes are called tectonic earthquakes. The point of origin of an earthquake is called the focus, while the point directly above it on the surface of the earth is called the epicenter. Owing to the strong vibrations around the point of origin, the degree of destruction is greater around the epicenter. The branch of knowledge that deals with the study of earthquakes is called seismology, and the experts who study seismic waves are called seismologists. There are three types of seismic waves that spread in all directions from the focus. They are the P, S, and L waves. The compressional waves are the first to reach the earthquake recording station as they travel 1.7 times faster than the shear waves and are therefore called primary or P waves, while the shear waves are called secondary or S waves. The primary waves cause the particles of rock to vibrate forwards and backwards in the direction of the waves. Secondary waves, on the other hand, cause the particles to oscillate at right angles to the direction of the waves. When P and S reach the surface of the earth, they get converted into L, long waves that travel along the surface, vibrating horizontally at right angles to the direction of the waves, called love waves or Rayleigh waves, as they also travel like sea waves. The most violent shocks and subsequent destruction is caused by the L waves. The instrument used to detect and record seismic waves is called a seismograph. The recorded material appears like a graph and is called a seismogram. Based on the depth of their foci, earthquakes are classified into three types. They are deep focus earthquakes that occur at depths exceeding 300 kilometers, the reasons for which have not yet been identified. Intermediate focus earthquakes with depths of foci ranging between 55 and 300 kilometers. Shallow focus earthquakes with depths lesser than 55 kilometers. To measure the magnitude of the earthquakes, a Richter scale is used. The point scale is arranged in such a way that each of the units on the scale is equivalent to 30 times the energy released by the previous unit. While a magnitude of 2 is seldom felt, a magnitude of 7 indicates the lower limit of an earthquake that has a devastating effect over a large area.
Here it's coming up through the sidewalk.
うわ、中大丈夫あれ。In front of, I should say, the mobile home fire caused by the Napa earthquake. Unfortunately, 5 homes were destroyed because of this. And the big problem, as you can see pieces of the home falling onto the ground there as the fire continues to burn, was that the earthquake actually shattered some of the underground water lines. So firefighters had to lay hose almost the entire way throughout the mobile home park here, making it quite the firefight. You can see, unfortunately, again, 5 homes, 1, 2, 3, 4 is back there, and 5 the firefighters are still working on as we speak. 5 homes gone, and as you can imagine, the challenge in all of this was the fact that mobile homes are so close together, less than 20 feet apart, and unfortunately they really aren't conducive to stand up against fire. These homes are modular homes, and they don't have a whole lot of insulation or firefighting material inside. So when one started, it didn't take long for the rest of them to go up. Once firefighters got a great handle on this, they got the rest of the area under control.
We heard a huge explosion downstairs. We ran up to see what it was. And I guess they didn't get the fire under control because there it is. Burning. Oh, I hope everyone made it out of there okay.
के गरेको आउनु छ नि उताबाट आउनु हल्लिरहेछ है हल्लिरहेछ बाटोमा सर Madonna Santissima! Via per favore, via! Filippo! Fuori! Di drammatico. Madonna! È pazzesco! Incredibile! Correte! 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 Madonna Santissima! Guarda come si muove!
All across northern Japan, they felt it. A violent magnitude 9.0 earthquake on March 11, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next: run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesanuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall into Kamaishi City. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan and one of the 5 largest recorded in the world. More than 28,000 people are confirmed dead or missing. When 2 tectonic plates push together under the sea, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. With the upward motion, a series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice. But as the waves enter shallow waters, friction with the ocean floor lowers the wave's speed, but raises their height. This video is from a Japan Coast Guard ship confronting a tsunami wave in shallow water on March 11. And a rare view from the air, video of a tsunami wave approaching the shoreline. In this photo, the ripples of tsunami waves are seen moving upstream in the Naka River at Hitachi-Naka City. New technology left an enormous amount of visual evidence for study in years to come, and can perhaps help us better understand the power of earthquakes and tsunamis and prevent loss of life in the future.
In just moments, roads turned to quicksand, swallowing cars and swamping suburbs.
Oh, it was straight after the earthquake, mate. It was frightful.
This process, called liquefaction, has left much of the city a soggy, crumbled mess.
But the liquefaction, I mean, the suburban streets are like rivers.
You'll see these ladies over here, they're just sinking.
The silty, saturated layers of soil just below Christchurch were so severely shaken, they liquefied. And with much of the city built on soft earth, seismologists believe the phenomena has heightened the devastation.
Construction workers get alarmed after the ground underneath them turns into a thick ocean of saturated soil. This is pretty trippy.
Here, hold this and just watch, just shine right at the bucket.
Wow, that's fucking...
This is Dabu7. I want to share with you guys here just a quick clip of the liquefaction that took place in Indonesia, showing exactly what happened to the landscape from this earthquake that took place there. Look at this from satellite imagery. This is what happened to the land as it just gives way, like a massive landslide. And this whole region, which was houses, farmland, and everything else, gives way. And you would think, to see something like this, there would have to be a massive wall of water pushing in. Well, this isn't the case when you talk about liquefaction, where the earth becomes liquefied pretty much and starts to shift, as you're seeing here. But it's not every day you get to see this process, this magnitude. This is why so many people lost their lives and are still missing in this region. Wanted to make sure people seen it for what it was, because this can happen anywhere.
Ya está. Ah, esta está suelta. Sí. Esa pared de ladrillo,
Este edificio se movió horrible, horrible, tronó horrible. Que se salgan, la pared se rompió. Que se salgan. Que se salgan, se va a caer, se va a caer. Dios mío, Dios mío, Dios mío, Dios mío. Dios mío, Dios mío, Dios mío, Dios mío. La gente. Dios mío. Ay, no, Dios mío, Dios mío. Ay, Dios mío. Ari. Dios mío.
¿Estás bien, Fer? ¿Lo grabaste? Pues sube. No mames la gente, pásense,
Sí,
por
no,
favor.
ya sé. Güey, nos salimos del Conde. Ah,
a
exacto,
tiempo.
güey.
Sí.
No, ahorita ni siquiera
Y luego está uno incomunicado. Se cayó.
Condesa, se cayó un edificio literal, vamos a ayudar, güey. Vamos a ver, se cayó todo este edificio.
Señores, me acaba de tocar el temblor aquí en Cuernavaca. Muy cabrón. La carretera se cuarteó. Se cayó un puente. Muy peligroso, se sintió horrible. Ahorita que venía manejando. Miren cómo quedó. Se acaba de caer el puente hace unos minutos. Por poco y me toca.
Vámonos, vámonos.
¿En qué podemos ayudar?
Sí, pero es que hay peligro de explosión. Vamos.
No mames, esto se cayó.
Los vamos a ayudar, pero espérense ahí. Tranquilos, tranquilos, ahorita subimos.
Oh my gosh. This is a bad idea to be on this boat. I just don't want my phone to get bad. I don't care about my life. I don't care about my life. I just care about my phone. Oh my god.
Oh, you're recording this, right?
Oh. Oh my gosh. I'm on the end of it on 1985 day.
Yeah, but yeah, that's the crazy thing.
Yeah,
That's
no,
why
no,
I'm
no,
amazed.
Holy shit.
That is why I'm amazed.
This is the most interesting thing that's
Yeah,
happened.
I mean, this is surreal. This is fucking surreal. It's amazing. It's surreal. What are the odds? You know?
Vamos a la esquina, se va a caer. No mames. No, no mames, pensé que no estaba Sofi. Yo también. ¿Por qué no sonó? No mames. Sonó cuando ya estaba sonando. Okay.
No, no. Ya. Ya. Yo creo que cuando empezó a temblar se salió.
So this was some videos which are related with the earthquakes. Okay, this topic we will going to continue after 2 weeks. In that, I will explain all these points in detail. Okay, so thank you for cooperating today. We will continue the our continuous points in our upcoming lectures on Saturday. Okay, thank you.